Good morning, everyone. I am very happy to see that the participants, more than enough, have joined here in this course. This is a Gyan course on nonlinear continuum mechanics. So the Professor R.C. Batra is here. That one of our dearest colleague, Professor Sanjay Gupta, right besides Professor Batra, then right to Professor Sanjay Gupta is Professor Abhijit Guha. So, Professor Batra will take the class throughout the week in this classroom only. So, let me ask Professor Gupta to deliver some inaugural speech. Professor Gupta did his PhD from the Technical University of Delft, Netherlands, and he is the man of biomechanics in the country, and he is the first conductor of Gyan course of the country. So, I request Professor Gupta to inaugurate the session. Okay.
Hello. Thank you, Professor Roy, and welcome Professor Batra to our institute. I also extend my warm welcome to the participants of this GAN course on nonlinear continuum mechanics. Well, incidentally, I had the opportunity of delivering the first GAN course in this institute. This sort of course is unique in the country, the Global Initiative for Academic Network, which originated actually from the international summer winter term courses, and the brainchild of this the originator of this course was our director, Professor P.P. Chakravarti, whose brainchild was the GAN course. The whole objective of the GAN program was to expose the young researchers and PhD students, as well as also scientists who are embarking upon a new advanced field of study, to go through the basic material content of the subject, which is difficult for the students and the scholars to study from just studying from journal papers or attending conferences. So, if an expert from a foreign country comes and delivers lectures as well as tutorials, in a very short time the students or the researcher can get a comprehensive knowledge which he or she can utilize for further study. In this way, the level of scientific research and knowledge can be greatly enhanced. This was the whole idea of offering the GAN course. Alternatively, as we all know that we professors sometimes visit a foreign country and spend, say, 1 or 2 months during the vacation time. But in that case, it is a benefit for the faculty member, not really to the students. So, this is a very clear, with a very clear objective, primarily towards the benefit of the young researchers in the country, to offer comprehensive knowledge about advanced field of study. Please note that GAN courses are not meant for basic knowledge, basic courses. It is always the advanced field of study, advanced research topics, led by an internal expert an international expert from a very eminent institute outside this country. Of course, the coordinator has to be expert in that field of study who actually coordinates this whole program in a particular field of advanced study. So, I hope you will enjoy the course and you have to be a little bit serious because it is like a classroom teaching. So, you have to have lectures, we will have lectures, we will have tutorials and try to gather as much as possible knowledge during this week, so that you are confident in taking up problems for your research program, whatever be the research, it may be a PhD study, or it may be postdoctoral, it may be your ongoing study. So, for me, it was about 2 years ago that this GAN program started, 30th November 2015, and I belong to more in the biomechanics field, more solid mechanics, biomechanics, but there are participants from all over the country, and that field is actually very less established in our country, unfortunately. But after doing the course, even today after 2 years, the participants keep contact with me and they feel confident in reading journal papers that are published out, of late. Otherwise, it is very difficult for them. What they have given me the feedback that earlier it was very difficult for them to understand many things, because see, the research is an ongoing thing. It's a evolutionary thing. So, what has happened 20 years ago, it may be very basic, but it may not be well documented in form of textbooks, in form of easily available reading material. So, if we can deliver a lecture in a very comprehensive way, in a systematic manner, the advanced field of study can be introduced to great benefit to the students. Thank you very much. Enjoy the course.
Professor Gupta very nicely narrated about the Gyan course, and it is really true that in a comprehensive manner, if a very tough subject can be introduced in 7 days, it will be very helpful. That also I feel, because all of you can recall the preparations for any competitive examination. Initially, it was appeared that it is a course of 2 years course. Later on, you have prepared such that it become like 6 months course, then 1 week, then even 1 day. So, similarly, whether the continuum mechanics can be taken inside in your brain in 1 week or not, that should be tested, and I hope that Professor Batra will be able to generate that confidence that in 1 week you will feel like that I know continuum mechanics. That I can assure you. Okay. So, now I am introducing Professor Batra. Professor Ramesh Batra is the Clifton C. Godwin Professor of Engineering Science and Mechanics Department at Virginia Polytechnic Institute and State University, Blacksburg, USA. He has successfully mentored 36 PhD, 19 MSc and nearly 60 postdoctoral fellows, with whom he has published in reputable, referred and widely read journals 420 papers, of which 40 are single authored and about 300 have 2 authors only. His publications have received nearly 15,500 citations with an H index of 66 on Google Scholar as of today. His book Elements of Continuum Mechanics has been adopted at many universities. His honors include a 2015 ASME Honorary Membership, the 2016 ASME Robert Henry Thurston Lecture Award, a Virginia Outstanding Scientist Award 2011, a Society of Engineering Science 2006, like this. So he has many such laurels and awards I know, that he did not mention in this short CV. He has been teaching courses on continuum mechanics, nonlinear elasticity and the finite element method to PhD, MSc and postdoctoral fellows since 1974. So I request Professor Batra to say something. Yeah.
Good morning. Thank you very much for the kind introduction, and thank you for the inaugural address. I'm honored to be here, and I will try my best to communicate with you in as simple language as possible continuum mechanics. I think most of you are engineers, so you started learning statics in your first semester class. So continuum mechanics is like statics. It's basic course that one needs for research in any field you like. It could be biomechanics, it could be fluid mechanics or solid mechanics, geotechnical engineering, structural engineering, fluid structure interaction, blood flow. You cannot, if you wish to progress in the research, and I'm prejudiced because I teach continuum mechanics, so I think you should take it with a grain of salt, but it's as basic as teaching algebra in middle school. So the knowledge, a sound knowledge of continuum mechanics will help all of you, including me, in the research and education. So I think that's, with that I basically have said whatever I can say about continuum mechanics. So it covers elasticity, viscoelasticity, nonlinear elasticity, elastoplasticity. Those are sub-subjects in my opinion. Unless you know the basic part, unless a child knows how to walk, a child cannot climb stairs or steps, right, or run. So it's like that. If we don't know continuum mechanics, we really cannot do excellent work in even plasticity or fluid mechanics, even though most people think continuum mechanics is only for solid mechanics people. It's not true. So it's certainly not true. And if you wish to do fluid structure interaction problem, which is really but that's what our body is. I mean, the blood is flowing, is fluid and it's flowing through the arteries, is fluid structure interaction problem. So if we get plaque, like the deposits of calcium in the arteries, then the blood flow is hindered. I mean, it has to be diverted. Again, from arteries you have veins. So basically you have two pipes joining together. If you think of like say sewer pipes, it's roughly that way, but not, I hope it's not sewer flowing through the arteries, but blood is also a non-Newtonian fluid. And now the challenge is, how do you simulate blood? I mean, it's a fluid, but it's not like water because there are red cells flowing through it. And do you wish to account for those? It all depends upon how sophisticated a model you wish to develop for your problem. Okay, so and I hope that over the next 6 days, because this course goes from today through Saturday, you will feel comfortable in asking questions. Please don't hesitate. I mean, it's a two-way street. Unless you ask questions, I may or may not be able to figure out whether I'm communicating with you or not. Most of the time I can guess from your faces whether whatever I'm saying is making any sense or not, but if somebody is sitting at the back, I may not be able to guess right. So there is I think I will strongly encourage you to ask questions. Wherever there is doubt, please speak up, both in the class and outside the class. And as you very nicely said, don't hesitate to ask questions. And even after this course is over, please shoot me an email if you have any doubts or questions. Okay, good. Thank you, and thank you for being here. I forgot to thank the organizers. Sorry, but Manas Ray, Professor Manas Ray and I, we have been working together for, I don't know, at least for 10 years or so.
2006.
Huh?
Since 2006.
2006. So my guess is right. It's almost 10 years, right? Well, it's 11. Okay. And he has been very kind to me, and I think we have done some good piece of work together. And I sincerely appreciate all three of you for organizing and taking care of all of you. It's a lot of work. You know, most of us don't realize that organizing something is a lot of work. It's one can say it is equivalent to organizing, say, a birthday party because of the number of people here. But if it were a large crowd, then you can say it's equivalent to organizing a marriage. And you know how much preparation it takes? Those of you, I guess by looking at you, not many of you have been involved in those activities, but it takes a lot of effort. And when you will get married, you will see how much work your parents have to do. And that's what it takes to organize this course, because people call him in the middle of the night. Where is going to be the course? The poor guy has to answer you, right? So it's a lot of work for him, and I sincerely appreciate all of you and the institute and the central government, because they are funding it. There's a lot of investment. You may or may not realize it. So I know you are paying, or your company is paying, say, X number of rupees, but the central government is paying a lot of it. They are paying for my travel time, so like travel expenses, airfare, and they are paying me an honorarium. Also, there is an investment of time on my part, because I'm away from my family for a week. So unless we make full use of it, we are really not exploiting the resources you have. You have an excellent opportunity, and I have an excellent opportunity to interact with you. So the hope is that we will communicate well with each other and benefit from this opportunity. Yeah, please, I think you want to say something. Go ahead, it's okay. Well, thank you very much.
Thank you, Professor Batra, for nice introduction and encouraging the participants. Now I am introducing Professor Abhijit Guha. So incidentally, I don't have any short CV of Professor Guha, but let me introduce Professor Guha by myself. So I was knowing Professor Guha since long back, but he joined this institute in 2009 only. He is PhD from University of Cambridge. And he is an expert in fluid mechanics. That I knew that he solved several breakthrough problems, and since then I was very much fascinated to see Professor Guha. So who is Professor Guha? He is also graduated from my alma mater. So and we are now very good friend also, friend come colleague. So I request Professor Guha to deliver some speech, and he is here as the guest of honor. Okay.
It is a great honor to be able to address you and to be here. Now, when Professor Ray asked me to present something at the beginning of this course, he said about half an hour. So, I decided 3 subtopics, so approximately 10 minutes each. The first is I would try to explain that how fortunate you are to be in this course, because 2 very eminent people will be delivering this course, and what benefit you may take home. In the second part, I will try to give my vision of how you can utilize it in delivery of your own research, because unless if you only learn and do not deliver yourself, then it is not going to be very useful. And in the third part, I will try to make some comments on the nonlinearity aspect from my own research experience. As Professor Ray has already mentioned, I work in fluid mechanics, and hopefully those comments would be complementary to whatever you will learn over the next 6 days. So, this is the route map. So, the first, which is why attending a course of 2 global experts is important for you. And you know, I mean, I think you will face very serious equations and complex matter over next 6 days. So, if you feel like laughing during my presentation, please laugh. Okay, there will be some humor. You do not have to be very stiff. I just wanted to loosen you up in this half an hour speech, so that this benefit becomes increases. Now, the first part I said that why attending lectures or seminars of top people are important. So, I will try to present it from my point of view. You see, I have started with a quote from Sir Hans Krebs, who was the Nobel laureate in physiology or medicine in 1953, and all of you have studied in your school level biology the Krebs cycle, the citric acid cycle, which is important in releasing energy inside cells. And while inaugurating the Department of Biochemistry at the University of Newcastle upon Tyne, he said this, for me this sentence actually epitomizes the importance of this course. You see what he is saying, every word is carefully chosen. You see, when masters construct their sentence, how they do. Scientists are not so much born as made by those who teach them by research. You notice, that means if you want to learn, become good scientist, you have to learn from a good teacher who is also good in research. And there has always been some talks, you know, that at Cambridge University people are busy in research, so they will not be teaching, and yet every national survey conducted by the government agencies, Cambridge has come at the top of teaching as well as research together, which argues for the perpetuation of centers of excellence. And this, I believe, when I came back from after teaching for a long time at 2 top institutes in United Kingdom, I had to justify. And I thought, and many people told me, that there may be scarcity of physical resources. Coming to India, I have to admit there is no scarcity of physical resources at top universities. In fact, some of the top institutes in India can afford such things which Stanford or Cambridge cannot supply through central fund. However, there is a great scarcity of human resource, unfortunately I have to say, in a country of 120 crore people. And that is why in the second part I will say how I think you should be able to contribute, because you are still young. And incidentally, this is also published in Nature, and later it was reproduced in Physics Today, from where I first read this article some 20 years ago, and I still remember. And he was saying, how do you measure excellence? and then he was saying that maybe Nobel Prize is an indicator. So then he counted from 1901 to 1963 all the Nobel laureates in physics, and he showed that they all belong to 4 or 5 families. This is what he is saying, perpetuation of centers of excellence. You have to be working or in touch with a great man in order to be great. It's clear. The importance of learning from great masters, I will give 1 or 2 more examples. So after joining India, this IIT Kharagpur, my main effort has been to create human centers of excellence. And if you talk to my PhD or MTech students, you will see that they are very distinguished. Whatever is their background, it does not matter. One of them is sitting there, feeling very shy. But you know, my purpose is sitting in IIT Kharagpur, they must reach Stanford Cambridge standard. One cannot give these small arguments, oh, it's a small village, 120 kilometers away from Calcutta, we are natural disadvantage. No disadvantage. If we are in this business, we must try to become the top, and it is possible if we try in that way, if we have that aspiration. So there was a design project in our MTech course, and I was leading one group of students. So I decided, A, they must become engineers, that is, they cannot do some simply pen and paper calculations, they have to design, build and test an instrument during that design course, then they will become engineer. At the same time, I thought I must also inculcate this the love for great masters. So I chose a topic of an experimental setup which was set up by G.I. Taylor, and as you know, he is one of the greatest fluid dynamicists of all time. So I then sent the students home and I said, you do some research. So what they will do, they went to Google. Google is the best teacher these days. They never read any textbooks or journal papers, Google. So So after 2 weeks they come back. I said, what have you done? Nothing. So then I said, please read. So I gave this reference. Please read from the master. Read G.I. Taylor's own paper, which is published in Philosophical Transactions of Royal Society, very prestigious journal in physics, and also it publishes in engineering science. Then 1 week went, I know that they will not read. So then by that time I had downloaded. Next meeting, I have this 50-page paper printed. So I said, have you read? They said, no. I said, okay, now I will read and you listen. So I started reading and tried to show. You see, this is a very complex mathematical analysis. I hope you will go and see. I am only doing solid mechanics, continuum mechanics. No, great master, please see this paper. You will be inspired. And you see, it is a mathematical paper, but you see the attention to details of practical aspects. This is my summary, why I am so touched, how the instabilities have grown. He has drawn his own sketch, and how detailed the sketches are, you see. This is how, so if you take 2 cylinders and then they are rotated, bearing some relations, inner rotation and the outer cylinder's rotational speed and diameter ratios, and you have to choose the gap carefully, and then you can show these see these instabilities, because fluid mechanics is non-linear. I will come to that part. And then I said that they have to build the machine, the device. Have you seen any paper published in last 20 years which gives this sort of construction? Sorry. This sort of construction details by a mathematician, applied mathematician. He has done this. And then I know they will not read, so I started reading. You see, in order that this might be minimized so far as possible, the inner cylinder was fixed on a mild steel shaft A of large diameter. So he wrote up to this, and then he reflected and thought, oh, some of my readers may not know what do I mean by large. He said 3 by 4 inch, because if you don't follow these relations and if the vibration is there, then you will not be able to see the fluid instabilities. So, if you have chance, you come to the energy systems lab in the mechanical engineering, you will see how our MTech students have built this machine and tested, and we videoed and we could see some of these people. It is not easy, it is not simple. Same MTech students who cannot open their ballpoint pens sometimes, because they are not engineers usually, only theoreticians. No? So, this is the point of learning from masters. Then Professor Ray asked me to narrate some stories of this attending lectures and seminars by great people. Cambridge is a very rich source, and I attended, and if you visit my website, I have given many more details there. All the greatest people in all fields. What this field will do to me? If I attend Stephen Hawking versus Roger Penrose, how is going to help me in mechanical engineering? It does. Because if you just sit near Swami Vivekananda, you will be a great man to some extent, definitely so, because you are thinking only about great things inside, not trivial things. So, some James Lighthill, for example, one of the greatest applied mathematicians of all time, if you have chance to read any of his articles. So, I went to his talk, and he was trying to analyze the mathematics of hearing. So, he drew 2 flexible tubes, he was saying fluid structure interaction, then he wrote Navier-Stokes equations. Of course, it cannot be solved, nonlinear, very complex. So, he cancelled terms, only a genius can do. Ultimately, he kept only the few terms which mattered, which he could solve analytically, and from that simple analysis he showed that how our ear can hear over a very large frequency range. You think of it, 10,000 hertz, and very large range in loudness, and then he threw this challenge, you build an engineering device which can do it. So, if I have not gone to attend that seminar, how would I know this and be able to tell you this excitement 30 years after? Michael Ashby, you possibly know Ashby's material selection diagram, Ashby and Jones. So, after dinner talk I went there, and he said, let us design the weeping willow. You know these willow trees which grow beside the, and they usually droop down. So, he took the normal stress deflection condition, and then he analyzed moment and like the usual design practice, and then he went, and from his material selection diagram, it gives the best material for this loading condition is wood. Can you imagine how? And then he said, so God was correct in selecting the material for the weeping willow. But then at Cambridge University, there are other people, there are doubters, the critic, the referee. So, one man raised his hand. He said, as far as I can see, the loading on the leg of an elephant will be something similar. He said, oh yeah, actually if you go to my diagram, bone has also similar material. So, it just happens animals have evolved with this bone structure, and the plants have gone the woods route. But it is interesting, Fox Williams, FRS, fluid dynamics of snoring, you think of it. So, he had his postdoctoral student and an experimental rig, and he was altering the experimental rig then and there, and to show what is the effect. So, he found, and it was being conducted in conjunction with doctors in Addenbrooke's hospital. So, he found that the snoring, the main problem is near epiglottis, there is a difference of pressure above on the 2 sides of a membrane. So, the doctor in Addenbrooke said, oh, it is simple, I can solve it. So, for really problematic cases, because snoring can be a matter of argument, amongst families, so much so that they may separate. It is very serious matter, particularly in the West. And so, the doctor said, so in such serious cases, so they drilled a hole that equalized the pressure. They were not snoring, wives are happy. But then the patient is not very happy, the doctor says, because sometimes back they come back and say, actually doctor, there is a problem. What is the problem? Problem is when we drink tea, when I drink tea, sometimes it comes out through my nose. Then Fox-William says, okay, I have to change the mathematical model. So he took a semi-infinite plate and he did something to increase the stiffness of the plate. Vibration frequency altered, and he was then playing the sound, sound reduced. So the doctor took this, oh, that means I have to increase the stiffness of those tissues. You know what they do? They do a sandpaper. Sometimes this medical practice, and Addenbrooke's hospital, one of the best hospital in the country, are very rudimentary. They took a sandpaper and they would file it up, and it would be bruised, and when it recovers, you have noticed that the stiffness of the skin increases. So that reduced the snoring to some extent. This sort of William Hawthorne, he was talking about how Frank Whittle discovered jet engine. You imagine the excitement, learning from the horse's mouth, and he had and he was an engineering student at Cambridge University, a third-year student, when he built this. When he founded this a private company, he had to raise money because government was not giving him money. So ultimately these military people came for a demonstration. So he put his gas turbine engine on the back of a truck and started the engine, and the truck started moving in the opposite direction. So the military experts were satisfied. He said, okay, we will give you money, but tell me, we have a doubt. Because the gas turbine engine is rotating, how does the air know it has to go from this way and that way and not the opposite way? So apparently to this question, Whittle said, actually, General, I put an invisible placard here this way. So a sign is there. Anyway, I don't have time. Edward Wheaton, perhaps the highest H index amongst living physicists, 190. 1,86,268 citation. He holds the Einstein's chair at Princeton, and very interestingly, he has a history BA. He has a BA in history, and then he revolutionized with string theory and quantum gravity. Now the second part, how you can contribute. On this, I gave a very full talk, much fuller talk at Kanpur IIT recently. I will only, and there I gave 10 commandments, what our young researchers need to do in India so that Indian universities also become Stanford and Cambridge in a reasonable time. And we have to change our current model. I am a firm believer in this. If we do more of what we are doing currently, we will not become Stanford or Cambridge. So I have identified 10 principles, basic principles, how we can do it. And here I will discuss only the first 3 because I have time limit set. The first one, I have given 3 pictures. Lord Buddha sitting under the Bodhi tree, Nikhil Banerjee playing the sitar. How my PhD students are becoming Stanford standard, If I say Nikhil Banerjee playing sitar at 11 p.m, now he is teaching in another institute, he will go and listen to Nikhil Banerjee. Not asking how will it help me in fluid mechanics. It helps. He told me it helped. So you also listen, it will help you. And Albert Einstein in his study. So the question, what is common in the following 3 pictures? And usually I show this sequentially, but here the technology has allowed me to give you the answer also with the question. So there is no thought process. I have given the answer. Each one is doing sadhana. Sadhana, the word, was invented in India. Unfortunately, it is being done only in the West at this moment, and I will show some examples. What do I mean? So my principle number 1 of 10 commandments, one must do sadhana in order to be great. There is no shortcut to excellence. To do sadhana, and I have given a subclause, to do sadhana, one must spend uninterrupted quality time of substantial duration at a stretch. if you read surely you are joking, Mr. Feynman, you will see Feynman is saying he will go in and disappear in the one corner of the library of Caltech when he is building his theory, so that nobody can find him, because he says building a theory is like building a castle with pack of cards, and somebody calls him Richard, it breaks, he will never be able to build it again in the same manner, theory is gone. And like you, I also thought how our current excellent students are doing their research. So, I went in Google and typed excellent PhD student. Google gave me an answer. All the modern gadgets, very well equipped library, the finest laptop, mobile phone, he is smiling. Now, I go back and tell you, Buddha has sat under the tree for 20 years. He is about to receive his Bodhigyan, and then the Nokia tune. Can someone play for me? Can you imagine what will be the case? He will get Bodhigyan, 20 years of sadhana gone, gone. So, I am not saying that it's not the mobile phone is a very useful gadget, but it makes sadhana impossible. You will never be great scientist if you keep in your pocket a mobile phone when you are doing serious research. 3 hours, put it out. And then if your father or mother complains, don't give my name, but you have to take responsibility. The second, one must have the passion to find the truth, and I said the sadhana is being done in West. I have given 2 examples. Barry James Marshall, and I have said CV will grow as a byproduct, not as the principal objective. If you are great, you will be great, everything will be fine. And if you cannot play good football and you are only finding how to showcase, it will not work. People will find out one day or other. Barry Marshall, if you ask anybody how this stomach ulcer is caused, everybody will say stress, masala, reduce your ghee intake, all those things. Doctors are still saying this. Barry Marshall thought no, it is caused by a bacteria, and its treatment is with an antibacterial antibiotic. And our common belief will be if you take antibiotic, it will increase stomach ulcer, because with antibiotic they prescribe antacids to cool down the stomach ulcer. Nobody would believe Barry Marshall. So, what did he do? He took a petri dish full of cultured bacteria. I have given the name of the bacteria, Heliobacter pylori, and he drank it, and he developed stomach ulcer. So, he could have died. The death is what? Nothing. Everybody will die. But he has discovered the cause of stomach ulcer, for which he was given the Nobel Prize in medicine 2005. It is not coming cheap. He was ready to die for the cause, actual death. I have given another example, Perelman. The Clay Mathematics Institute has identified 7 problems, most important problems in mathematics, and they say if anybody can solve $1 million. One of them has been solved by this man, the Russian mathematician. You will not know about him. He does not meet any journalist. He does not work in any university. Privately he was solving. And then in 2006 he was, because he has solved a millennium problem, given the Fields Medal, which is equivalent to Nobel Prize. He said, I don't need it. Why? Because he said that because I am not that great, he said first, I am not that great. Second, my contribution is based on Hamilton's contribution. Can you give Fields Medal to Hamilton? How can I get Fields Medal for a work which is mainly Hamilton's work? How great this man. He was given this Clay Millennium Prize, $1 million, rejected, don't need. And you see what he's saying. And this is like a poem, emptiness is everywhere and it can be calculated. Emptiness can be calculated, he is saying, which gives us a great opportunity. I know now how to control the universe. So tell me, why should I run around for $1 million? Principle 3, we should not just do small tweaking, follow-up work. we should try for. So, I am giving you the path, my belief. You do not have to accept, you think and then you discover, find your own, establish your own unification, generalization of ideas. This is what we should try. Having at least one theory, one experiment, one process, one product named after yourself, then you know you have become great. 400, 500, 1,000 papers will not. Having aspiration that one's work will find its place in undergraduate textbooks, just like when you open Newton's law we are reading, or Einstein's theory of relativity, like that. Everybody cannot become Einstein, but the aspiration, we must be at that level. I am not saying everyone will become Newton, but there is also no point of doing small tweaking. Now, the third part, I will finish in, as I said, the 10-minute stage. This is about nonlinear continuum mechanics, and you will, as I said, that you will learn the subject from two greatest exponents available. So, I do not need to talk about the core material, but some complementary comments. Solids may have material nonlinearity, because Hooke's law, is based on small departure. If you take the Lennard-Jones potential and take small departures from the equilibrium position, you can show that stress is proportional to strain. But what happens if that displacement is larger? So, material nonlinearity. So, the stress strain curve also, even in the elastic limit, bends. Large deformation is another. Fluid mechanics, which is my area of research, everything is nonlinear mostly. Why? Because of this term in the Navier-Stokes equations. This is the nonlinear term, acceleration term, and in most situations it cannot be neglected, and that causes, and that gives all the beauty and the complexity of fluid mechanics. So, I will give one or two examples and see. So, this is a recent work that we have done at Kharagpur IIT with one of my students, Sayantan Sengupta, and I said that we need to do something new. This work, so we did not even know how to draw the pictures, because nobody has written on this topic before. What are the things to look at? So, there is a well established solution by von Karman. If you have a rotating disk in a fluid, then how the fluid, so usually the fluid comes from the top and it goes towards the outer periphery. These are the pattern of streamlines. This solution has been given by von Karman. Now, we thought that what would and also in the literature solutions are available. If you have a static disk which is warm than is ambient air, then natural convection will take place, and in natural convection the streamline pattern is opposite. It will come from the periphery and go through the center as a plume. Now, we are combining, but combining how? Combining through this nonlinear equation, Navier-Stokes equations. So, there are many very stunning new results which you cannot could not have apprehended a priori. For example, the heat transfer coefficient, will it be enhanced or decreased? Because two mechanisms are now present, and we find in certain regimes they are added, in certain regimes it decreases. Or you see the other, I will explain this in more detail in the next slide. Some other very interesting details. You notice that these two streamlines I have drawn side by side, one goes like this, the other goes like this. Effect of nonlinearity, very small difference in initial position, the final outcome is totally different, totally different. And then there are many other things. You see, you get a hot patch of fluid which is hotter than the disk surface itself because of this convective migration. So, some of the ramifications of, because the fundamental equations of fluid mechanics are nonlinear. These are some of the characteristics of nonlinear flow. And as a result, a totally new subject has grown, computational fluid dynamics. Many people interpret it that solving fluid mechanics with the help of a computer. It is so, but my view is that it is not just that. because of that nonlinear term, a new subject has grown which has its own dynamics, which is not relevant for the actual fluid mechanics. What happens? That if there are errors in the solution, and at initial phases there must be errors, because of the nonlinear terms they may amplify, and so the task is how to dampen them, not so much that it alters the actual final solution, but the process of convergence is possible at all. It may be totally lost after few days, exception error, it will not work. And interestingly, if you see, I said that this is the most important term, this is a complex term, and Navier-Stokes contribution, because if you remove this, this is the Euler's, old Euler's solution, but this term is very well behaved, even though it is a second order term. There is no problem in modeling it, you can use central differencing scheme, no problem. In fact, it is so much so that in order to suppress some of the convective instability I said introduced by the nonlinear term, you may have to introduce artificial viscosity in the computational scheme. So, I was trying to solve the shock waves. Shock waves are where suddenly the fluid flow properties change, and these are areas of intense nonlinear activity, intense. And if the CFD tool is not very proper and you try to capture it very accurately, what happens that there is overshooting before the shock wave, then it comes down, and then there are fluctuations downstream. Then you put lot of artificial viscosity, and then the solution will be smeared. Then you will not know the exact location of the shock wave. So, a balance is needed. And in this, I have said that two-phase water vapor, this actually introduces a relaxation medium. You see the ramifications of nonlinearity. What is the relaxation medium? In an ideal gas, which you have learned so far, whatever frequency of sound wave you transmit, it will move at the speed of sound. But in a relaxation medium, the speed of sound is a function of the frequency. So, this is known as the dispersion effect, and it is known that this dispersion tries to make the tail longer, whereas the nonlinear effect tries to make it steeper. So, you see, I wrote a CFD code, developed a CFD code myself to compute first moving shock wave. I said that is a very challenging task in fluid mechanics in order to do it properly, and then in a relaxing medium. So, computing, and you see what is being done, see, absolutely sharp frozen shock. So, you know the CFD has captured that nonlinear effect, and then this tail because of the relaxation effect, relaxation gas dynamics. More recently, I have tried to capture the lung. So, very complex nonlinear, and the usual model was they were doing where the pipes, as Professor Batra said, these arteries and veins, this structure on a plane. But in fact, if you draw these things on a plane, there are two problems. One, that they will intersect one another after some time and you cannot continue anymore. The other problem is you cannot fill a space with such a structure, because ultimately lung is a three-dimensional object. So, we rotate it, you see. So, this is a, and the nonlinear. So, this Kaustubh is working on that, and this actually physics of fluids put this as the cover page article of the December 2016 issue. So, if any of you are interested, you can go and see the effect of nonlinearity in fluid mechanics. So, this is my last slide. You see what is the effect of nonlinearity. This is again my summary. Very important mathematician Laplace, in his work a philosophical essay on probabilities, he made this very important. So, I started with a Nobel laureate statement, I am finishing with a one of the greatest mathematicians statement, and there he says, you see, we may regard the present state of the universe as the effect of its past and the cause of its future. And intellect, which at a certain moment would know all forces that we set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit this data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. This is a very grand claim. Essentially, what Laplace is saying, that if you give me the differential equations and give me the initial conditions, I can predict the entire future. No need to go to the Jyotishis anymore. Laplace can do it for you. Problem. And problem originates from nonlinearity. If you try to write the equations for natural convection in a circular loop and then simplify the equations to some extent, one can arrive at the Lorentz equations. And in Lorentz equation, I have given the evolution of 3 properties. You do not need to know the details, just try to feel the essence: dx dt, dy dt, dz dt, and then I have also given equation. So it satisfies Laplace's condition. I have found the equations, differential equations, and they are very simple looking. This is, and then given an initial set of conditions, then it can be integrated in a computer. This is the result for certain values of the parameter, and you see what has happened. Basically, no pattern may be discernible at all, and the predictability is lost. Dynamical chaos has been the result. And I also said that the other consequence is that these are very sensitive to initial conditions. You change the initial condition by a tiny amount, and the final solution you won't be able to match at all. And then you think that, okay, I cannot find the evolution of x, y and z themselves. What about if I can find its average values? So that is possible. You take the average of these time dependent equations, and then for this simple set of equations you get a simple equation for time dependent. You see z bar is the average of z value. Do you see the problem? Time average of x, y, that is correlation of 2 fluctuating components x and y is now needed. That is not known. So what do? Okay, I take a moment of the original equations and then take a time average, and then what will happen? Then quantities will come x square y, y square x and x y z. This is known as the closure problem. Higher and higher correlations are needed. So even the average position cannot be predicted. That is the problem. Fluid mechanics, this problem is even more difficult and complex than this, what can be represented by the simple Lorentz equations. Turbulence, random like, but it is not totally random also, because there are coherent structures, there is some order. So it is not also a random function. This is the problem of turbulence. Energy cascade. So there are eddies of many sizes. The largest eddy, something of the physical domain, size of the physical domain, and they extract energy from the mean motion, from the average motion, and then through this energy cascade they send it through the tiniest Kolmogorov scale. So very small dissipative structures. So energy is being continuously lost from the mean motion and is becoming thermal random like motion of the molecules. Direct solution of Navier-Stokes equation is possible, but it is limited by the Reynolds number. You cannot solve for very large numbers, at least with the current computational resources available. And the reason I have already explained, because from the very tiny scale to the large scale everything must be captured. So it is very resource intensive. Then you say, okay, I will not solve all those fluctuating components, but I will solve some average quantities, just like I introduced there, Reynolds averaging. But it has the same problem as the closure problem. You have now higher correlations, xy and xyz and xy square z goes on in. So some sort of turbulence modeling is required. That means empiricism has entered. The other thing is that very sensitive to initial condition. Lorentz himself termed this as a butterfly effect. So journalists have transferred this idea to the things, a butterfly flaps its wings in Singapore, and 15 days later there is a tornado in California because of this nonlinearity in Navier-Stokes equation, simply speaking. This is why the long term weather prediction is not accurate. Short term weather prediction has become very very precise these days, because Navier-Stokes equation can be solved numerically these days. Previously 40 years ago that much computational power was not. Long term is still problem because of this nonlinearity. So do you see what is the problem? So what I am representing to you is a paradigm shift in science, because Laplace thought if you have the equation initial condition, everything is predictable. We are now finding that the equations are known. It is believed that turbulence is governed by Navier-Stokes equations. Belief. Maybe one day it may be proved wrong, but so far the indication is that it is an adequate equation. That means the system is deterministic, and still it is not fully predictable. So this is a paradigm shift. A similar paradigm shift took place in science when quantum mechanics was developed, because the certainty was replaced by Heisenberg's uncertainty principle, and the person who took part, very major part in the development of this quantum mechanics, Albert Einstein, was so uncomfortable that he spent a significant amount of his later life in trying to disprove it. So he will do some experiment, thought experiment, and he will write to Niels Bohr, and Niels Bohr has a standard letter, dear Mr. Einstein, your proof is wrong because of, only he will feel this thing, your own general theory of relativity, this. So Einstein's attempt to disprove quantum mechanics, but you see the problem they are also similar. The certainty, the certain world has been replaced by the uncertain quantum world, and similarly the nonlinearity in the mechanics has reduced the predictability even when the equations are deterministic and known. So Laplace's dream may not be fully realizable. Thank you very much for listening.
Thank you, Professor Guha. So Professor Guha delivered a very encouraging and inspiring lecture as well as the presentations, and maybe I will be motivated more also by his lecture. So it is really stimulating lecture, and now we should go for a tea break. So let us go outside, have a tea, and just after the tea break the class will start. So it's a 15 minutes break.
You know Bengali and I know Hindi, so we may or may not be able to communicate. But in mathematics does not lie. Most of the time it has only one meaning. So if we communicate in mathematical language, that is unambiguous. So that's the first part, to develop a common language between all of us, or amongst all of us. I do not know how many of you are familiar with the index notation. Some of you probably are, and others may not be familiar. So we will go over the index notation quickly. When I say quickly, maybe in an hour or two. And so starting, say, this afternoon, or so, then I will be using only index notation. There are a couple of reasons for index notation. One is, instead of writing, say, 3 equations, I have to write only 1, and then the remaining you can see right away. So it's a shorthand notation. Basically that's about it. It's a shorthand notation. The mathematics background we need is only what you learned in first year of college, which is differential calculus, integral calculus, matrix algebra like multiplying two matrices and inverting a matrix. That's about it. You probably have learned eigenvalues, how to find eigenvalues, eigenvectors. And so the mathematical background required is very minimal, more or less. But before I start turning that way, so may I request you to please turn off your cell phones. So this is not only here. Every class I teach, whether it's a short course or a regular course, I turn off my cell phone, which I already did. Mine doesn't do any good anyway, but okay, I turned off my cell phone and I ask all the participants in the class or course to turn off their cell phones. As you learned earlier, is sadhana. So one principle of sadhana or one basic requirement is that there should be minimal disturbances. So if you feel that you have an emergency call coming, it's better not to come to the class and take the call outside, because if your telephone rings, you are not only disturbing yourself, but you are disturbing others in the class also. And none of us has a right to disturb, say, 35 persons because I have an emergency. So it's unfortunately students don't like it. They give me very bad evaluation at the end of the year. We have that system. At the end of the semester, students evaluate teachers. So they always write, most of them write nasty things about my policies, that he doesn't let us use his cell phone and blah, blah. He doesn't let us come late, which is true. That I basically lock the doors from inside, that if the class is at 11 o'clock, it's 11 o'clock, according to that clock, not your clock, not my clock. Because otherwise we can always say, hey, my clock is slow or fast. So these rules I give them in writing. And one student asked me, he said, what if you will be late? Seriously, he asked me, what if you are late? I said, I will sit outside for it was 75-minute class. I said, I will sit outside for 75 minutes. You students stay inside, and whenever the period is over, I will leave and you leave. It's fine. So I will pay my punishment, that I will sit outside in the corridor. But fortunately, I have not been late, because I make sure that I reach 1 minute earlier. So, okay. Anything you want to ask before I start? I learned continuum mechanics from Truesdell. Now, if you really want to learn this subject, you should read, I will write his name here. Clifford Ambrose Truesdell. He has written, like Truesdell has written something like 20 books. 2 of them, classical field theories of mechanics and nonlinear field theories of mechanics. So classical field theories of mechanics and nonlinear field theories of mechanics are like Bhagavad Gita. Seriously, I'm not kidding. They are like Ramayana, Bhagavad Gita, Guru Granth Sahib, anything you like to say, or Quran. If we can understand those 2 books, the material in those 2 books, right, then you will have sadhana in continuum mechanics. And there are very, very few people in the world, including me, who can understand both books, the material in those 2 books. Now, I have not read all of those 2, but I have read the nonlinear field theories, some of it, not all of it. But anyway, so the bottom line is that if you wish to do sadhana in continuum mechanics, go to the library. These books are unfortunately little bit expensive. Like it could be, I don't know, 6,000 rupees each, but it's worth the investment. So, if you want to pursue research in continuum mechanics, which I hope at least some of you will do it, all of you use continuum mechanics every day in your lifetime, in everyday work. It's true. I use it, you also use it. We may or may not know it. Okay, so I think I need an eraser to, oh yeah. So please tell me if you are able to see at the back or not, because when I requested for a classroom that has a lot of chalkboard space, but because of the technology, I guess we are limited to this screen. So now I'm going to start with the continuum mechanics part or the index notation part. So we are all, most of us are used to using rectangular Cartesian coordinates. So we could say x, y, z. Here we say z, but in the USA we say z. Whatever, I don't know why. So if you take any vector, say u, so we write it as, maybe I should write it here. We write it as u is equal to ux I plus uyj plus uzk, where I, j and k, these are unit vectors along x, y and z axis, right. So I, j and k are unit vectors along x, y and z axis. Then ux, uy and uz, these are the components of vector u along x, y and z axis. But I have to write a long expression. So instead of using x, y, z, I'm going to change the names. So I'm going to say, instead of saying x, I'm going to say x1, x2 and x3. So it's not all we need is really 3 different names. Instead of saying x, y, z, we say x1, x2, x3. Now that itself does not help me, because I have to do one thing more too. Instead of saying I, j and k, I'm going to say my unit vector is E1, E2 and E3. So E1 has the same properties as the unit vector I has. So there is no distinction. Basically, you may say you have given a nickname. Instead of saying I, you are saying E1. But the beauty is that now this expression, instead of writing uxi, I can write it as u1, E1 plus u2, E2 plus u3, E3. It's a little bit symmetrical. I say it's u1, E1 plus u2, E2 plus u3, E3. Whereas previously it was uxi plus uyj plus uzk. There is no big change. No, we have not lost any physical meaning. Also, this thing I can now say I can write I equal to 1, 2, 3 ui ei. So I saved some more writing, right? And you heard Einstein's name a little while ago. The next is not given by Einstein, I think, but anyway, many people call it as Einstein's convention. So now we are going to adopt a convention amongst us, and this is more or less universally accepted. It's true among chemists, physicists, mechanics people, mathematicians, that if to save further ink, we adopt the convention that if an index now I here is repeated once, which means it appears twice in the same term, that is the key thing, in the same term, then we will assume that it is summed, and it is summed over the range of the index. Here we are writing the index goes from 1 to 3, and so with the summation convention then, so we will say we will not use that sigma symbol, we will drop it. I mean, sometimes you call your friends by a nickname, basically you call it by a shorter name. So it's something similar here, and so it's a convention now. It's a convention that most people working in applied mathematics adopt. It's true they adopt in fluid mechanics, solid mechanics, and maybe gas dynamics, whatever field it is, they do adopt this convention. So the key thing to remember is an index must appear only twice in the same term. If I write something like this, AI plus BI, this is not a repeated index because there is a plus in between. If I write AI BI CI, that's also garbage because I appears 3 times in the same term. So it's not, it has no meaning. Okay? Does it make sense? Now if I take another vector, say V, so I can write V I E I same way as I wrote for U. Also I can write as Vj Ej, because no j is summed, but we have an understanding that unless I tell you differently, both I and j go from 1 to 3. And same thing I can write k, Ek. I think most of you are familiar with the integral part. So x dx is same thing as writing y dy, is writing z dz, say 0 to 1. So the variable, so in this case x is playing a dummy role. In those cases the indices I and j, they are playing dummy roles, right? Now if I want to take the inner product, dot product, I don't know whether you call it dot product or scalar product or inner product, one of the 3. So they mean the same thing. So that means basically what I am trying to do is one of the things you can say I am trying to do is find the angle between these 2 vectors u and v. I want to find the angle between them, and one way to find the angle between them is take the dot product or take the cross product. So let's say I want to take the dot product. So that will be then ui ei dotted with vj ej. Now if you notice, I used I as a dummy index for u and j as a dummy index for v, because if I had used I for both, I would have gotten I, which is like 4 i's, and that will be meaningless. So now the dot product or the scalar product is between vectors, not between scalars. So what is this u1, u2 and u3? These are numbers like 1.1, or these are components of u along the 3 axes, but they have numerical values. They are not vectors. So, same thing about V, it is not a vector. So, this thing is really U I V j E I dotted with E j, because the dot product is between vectors, right. Okay, now what is the property of these unit vectors E1, E2, E3? What is the property of the unit vectors I, j and k? What is I dot j? 0. I think somebody said it's 1, thus I dot I is 1, but I dot j is 0. So, E1 dot E1 is 1, and E1 dot E2 is 0 and E1 dot E3 is 0. I can similarly write some more, like if I take now E2 dot E1 will be same as E1 dot E2, but E2 dot E2 is 1 and E2 dot E3 is 0. So, now I want to write all of these, because again these are going to be 6 of those, because E1 dot E2 is same as E2 dot E1. I want to save writing. Also, I do not want to lose communication. So, we introduce another notation, and this name is Chronicle delta, and this has value 1 if I equal to j, and 0 if I is not equal to j. People at the back rows, is the writing visible? Is it okay? So, all of these now 9 quantities, E1 dot E1, E1 dot E2, E1 dot E3, E2 dot E1, E2 dot E2, E2 dot E3, all of those 9 quantities are basically written in this equation. See, instead of writing 9, we have written 1. I goes from 1 to 3, then j goes from 1 to 3. So, if I and j or k, what any index is a free index, like I wrote here sometime little while ago, ai dot ai plus bi, and if I say this is ci, so I appears only once, ek bar, right, only once in each term. So, if an index appears once in one term, it must appear in each, the same index must appear in each term for this equation to be meaningful. So, in this case this one says C1 equals A1 plus B1, C2 equals A2 plus B2, C3 equals A3 plus B3. So, this is a short way of writing 3 equations in one. See, otherwise I would have written vector A plus vector B equal vector C, but or you would have written x component of A plus x component of B equals x component of C, but this is a lot easier than writing those 3 equations. We are not losing any meaning, okay, nothing has changed, it is just a short way. So, these days those shorthand stenographer jobs are gone. When I was your age, a part of the work of the secretaries or assistant, administrative assistant was taking shorthands. So, they say Professor Ray will dictate, he wants to write a paper. So, he will, instead of writing himself, he will dictate and the person will take notes and then go to the office and type. So, they in India they used to call it stenographer, but those jobs are gone now. this. Well, I think if you have gone to a medical doctor, doctor sees you, and then he or she dictates the diagnosis in a phone, cell phone, and then somebody types it. So, but nowadays you don't need a typist, because the software converts your voicemail into a written document. So, this is a shorthand for writing 3 equations, to make the long story short. So, this is a shorthand for writing those 3 equations, and this is a shorthand for writing those 9 equations. So, what is the property of this now? So, this delta ij is 1 if I equal to j or is 0. So, if you wish to write say delta ij in the matrix form is 1 0 0 0 1 0 0 0 1, because when I equal to j is you get 1, when I is not equal to j you get 0. So, in the matrix form is identity matrix, right. Okay. So, if you agree with that, some of you, at least if I read your faces right. So, what will be this thing equal to then? AI, very good, because this is A1, A2, A3, J is summed, I is a free index. So, when I is 1, unless J is 1, you will not get anything, you will get 0. So, J has to be 1, which means when I is 1, the only thing you will get here is A1. When I is 2, you will get A2. When I is 3, you will get A3. So, this is really a unit matrix or identity matrix post multiplied by a vector. So, you get the vector back. So, this thing is AI. So, what the delta ij does, it replaces the index j on A by the index I, by the free index I now. If you agree with that, then we can make more progress now. So, here first thing is we said EI dot EJ is delta ij, because that is the notation we introduced, Kronecker delta. Kronecker is the name of a person. So, that we introduced Kronecker delta. So, that is UI Vj delta ij. I is summed, j is summed. So, in principle this is sum of 9 terms. I is summed, so you take I equal to 1, then sum on j. So, you get 3 terms. Then take I equal to 2, sum on j, 3 terms. So, this is sum of 9 terms. Now, let us look at this delta ij Vj. Good, very good, Vi. So, this is Ui Vi. So, that is Ux Vx plus Ui Vy plus Uz Vz. That is what we learned in like vector algebra course. So, this again, as I said before, it is a shorthand way of writing this. So, in future then when we want to write u dot v, we will write Ui Vi. We will not write Ux Vx plus Ui Vy. Also, we will not use x, y, z. We will use x1, x2, x3. We will not use I, j, k as unit vectors. We will use E1, E2, E3 as unit vectors. So, one thing more before we erase it, or so we said we want to find the angle between vectors u and v. So, one is of course take the inner product, and the other is cross product, because inner product will give us the length of vector u multiplied by the length of vector v times cosine theta, and the cross product will give us sine theta. So, supposing if I want to take the cross product u cross v. So, difference between u cross v and u dot v is a scalar, but u cross v is a vector. So, we will get 3 components now. So, if I have this, so if u cross v is w, then w has to have 3 components. So, now I want to write this in index notation, and also you need to remember that one way to get u cross v is you write I, j, k, u1, u2, u3, v1, v2, v3, and now if you take cofactors, or this will be equal to I times u2 v3 minus v2 u3 plus or minus j times u1 v3 minus v1 u3 plus k times the expression, right. That is how we evaluate. So, we need another symbol, another notation, and that symbol is the following. It has 3 indices, epsilon I, j, k. So, these are 27 components. I goes from 1 to 3, j from 1 to 3, k from 1 to 3. So, 3 times 3 times 3. So, these 27 components have the following values. So, you write either in a straight line, or you can write in a circle, whichever way you prefer. So, it is your choice. When to remember, you can either write in a circular form 1 2 3, or you can write 1 2 3 1 2 3. So, if you write in a circle, so if you go clockwise, so if I is 1, j is 2 and k is 3, then the value is 1. So, if I, j, k cyclic permutation of 1 2 3. So, if you go clockwise, and if you have digital watch, you may not know what is clockwise, but I think that is not a digital watch. So, that the way those needles are moving, they are moving in clockwise direction. So, if you go 1 2 3 2 3 1 3 1 2, you can start from anywhere you like, but you have to go clockwise. So, 1 2 3 2 3 1 3 1 2, you cannot stop anywhere, you cannot say 3 1 1. Or if you use this, you go from left to right. You can start from anywhere you like. So, it is 1 2 3 2 3 1 3 1 2, then the value is 1. But if you decide to go in the opposite direction, counterclockwise, then the value is minus 1. So, we have covered 6 combinations now, 1 2 3 2 3 1 3 1 2, and if you go counterclockwise, 3 of those. The remaining 21 are zeros, and that is if any 2 indices are equal, then the value is 0. So, if the any 2 indices are equal, so if any 2 indices are equal, then the value is 0. Now, to convince you that I am not teaching you something useless, later on when we study how the bodies deform, we will need to know what is the new angle between line elements. So, the kind of problems we are planning to study are these. like if you draw a line here, you can draw either one line or two lines. So, if you draw one line, then you can, and I pull it, you can see how much of that line element will be stretched. Supposing I drew a line 1 centimeter long and I pull it, what is your guess how much it will become? Two centimeter, 3 centimeter, right? And maybe if my skin is more flexible, I can probably stretch it to 4 centimeter. You can see it. I mean, it's not, I'm not kidding, right? And now if you draw two perpendicular lines and I pull it, the angle between them can change a lot. So, this, when I say u dot v, that's what we will need to do, because we will need to find, first we will need to find where those lines have gone, because if I draw two lines, they were not, and supposing they are mutually perpendicular to start with, and I pull them, they are not going to stay perpendicular to each other, most likely, or highly likely they will not stay perpendicular to each other. So, I need to know where they have gone, and then I need to know what is the angle between them. So, if you, that's what is called a shear strain, the change in angle between two lines which were, say, initially perpendicular. So, to find the change in angle, we will need either u dot v or u cross v, depending upon your preference. So, that's why we are learning that. Okay. So, it's not, I cannot talk about stretch of a line element right now till we know a little bit more about this notation stuff. Okay. So, to complete my story here then, so this cross product, like we wrote here, dot product. So, the cross product we have similar thing, we have E1 cross E1. So, was E1 cross E1? 0, good, and E1 cross E2 is E3, and same thing I can write about E2, oh well, before that, E1 cross E3 minus E2, and then you start with E2, then write E2 cross E1, E2 cross E2, E2 cross E3, and so on. So, you have 9 of those. So, I now want to write all of those 9 into one equation. So, my claim is that all those 9 we wrote are really these. How do we check it? First of all, these are 3 equations. I goes from 1, 2, and 3. I is free index on both sides, same free index on both sides. So, these are 3 legitimate equations. Take I equal to 1. So, this will be then 1, 2, 3 Ej Ek. Oh no, sorry, wrote it wrong. So, this is J K. So, now if I is 1, right. So, J can be only 2 or 3 because otherwise I will be in this issue. If j is 1, then two indices are equal. So, I will get 0, and if j is or k is 1, same problem. So, this thing has to be then epsilon 1, 2, 3, E2, E3, and because this is summed, so it's 1, 3, 2, E3, E2. I think I goofed. I'm sorry? Yeah, yes, I think I goofed. Yes. Yes, I goofed. Sorry. So, what I should have done, like this thing is Wi is epsilon I j k u j v k. Now, I will show you that indeed this thing is whatever we got there. So, if no not quite. Let us see first this one, then we will see what I did wrong there. So, W1. So, it's 1 j k u j v k. So, again as I was saying before, j can be 1, 2 or 3, k can be 1, 2 or 3, these are summed, right, 9 terms. So, if you take 1, 2 k u j v k plus 1, 3 k u 3 v k. So, j we summed on j. If j is 1, then we got 0, so I did not write it. So, j can be 2 or j can be 3. So, this one then has to be 3, otherwise you will get 0, and here is it okay? Now, 1, 2, 3, 1, 2, 3, 1, 2, 3, that equals 1. This is 1, 3, 2 minus good. So, that is minus u 3 v 2, and that is basically what you have here, u 2 v 3 minus v 2 u 3. So, that is the first component, and then if you do the second component, you will get that j whatever is multiplying j, and if you do the I equal to 3, you will get the third one. So, I goofed when I wrote earlier, but so u cross v equal to w, that means w I is epsilon I j k u j v k. Does it make sense? But I do not need to do the second component, third component. Okay. So, let us see what other notation we need to talk about. So, we will whatever else we need, we will introduce it when we need it. So let's say let's talk about the example I showed you is pulling my skin now. So we want to study how we can measure changes in length and changes in angles between any two line elements. So first thing we need to identify is every point in my body. How many points are in a human body? How many points are in this piece? Infinitely many. We need to give a name that is immortal, it does not die, to every point in this body. How can we do it? Is the question making sense? So for every point in this body, we want to give a name, or for every point in your body or my body. This is more difficult than giving a name to each one of us, because like the population of India, I think maybe, I don't know, says 120 crores. So each one of us has a different name. Even though I see in the literature R.C. Batra, there are more than one. So, but that is not permissible for this body, because I want to be able to say that distance between these 2 points has changed, which means I need to know those 2 points. So any suggestions on how can I do that? I'm sorry?
Giving the domain and the coordinates.
And given the so I use, yes, you are right. I use a coordinate system, and in space, supposing this object is here and I use a coordinate system, I can find the coordinates of every point in this body, and they are different. I mean, that's the beauty, right? That those 2 points, every point in this body is occupying a different point in space. So I will call this as a reference shape. This is the shape from which I am starting. Now this shape may or may not be stress free, but I have not talked about stress yet. So we will say later on then. So basically we have this body, and generally in continuum mechanics, or most of the mechanics, we show it as a potato, aloo. I mean, this is a convention. I mean, so this is the shape, and I choose my coordinate system, but we just agreed we will write x1, x2, and x3. Also, if I say this is the starting configuration or the reference configuration, I'm going to use uppercase instead of using lowercase x. I'm going to use uppercase x. So that way I will know that I'm talking about the names of particles. The significance of this point P is its name is x. Will you like for me to say a vector is like this one, or put a underneath tilde? Sometimes like we show like this, other times like that. So, this one, when we did not have these word processors like words, we used to write like that. So, the typesetter, when he prints the paper for you, he will make it bold face, he will make it thicker. But these days there is no need to do that because we type for them. So, which one will you prefer, this one or that one? Because I have to show that one. Yeah. So, the beauty of these names is this particle P, every particle in that body never dies. It cannot disappear. I mean, you and I will die one day, but these particles never die. Also, another limitation is whatever we are going to study, we are not going to be able to do this kind of problem. Even though we teach you that we can solve fracture mechanics, but the presentation in this course, actually in most classical books, we cannot solve this problem. We make approximations to solve this kind of problem. So, we are going to assume that if two particles are occupying distinct places in the reference configuration, they will always occupy distinct spaces or distinct places in any shape. So, what I did here is I took one particle which was on the common interface and took it to two different places. So, it's like cutting me in, well, I cannot say in half, but cutting me, because I don't know from how the crack will go, and then saying, okay, this piece is also Ramesh and this piece is also Ramesh. That is not allowed in continuum mechanics. Whenever we do fracture mechanics problems, we make approximations, and when you make approximations, then you have to be worried about the quality of results. So, that's one limitation. By the same token, if my body is cracked, I cannot join it. So, I cannot take two particles or 2 points and put them into one place. So, both ways, I cannot take 1 point or 1 particle into 2 places, and I cannot take 2 particles into 1 place. In rigid body mechanics that we taught you in undergraduate class, we teach you collision of bodies, right? You transfer a momentum. There we say, okay, 2 particles are occupying the same place, but that's rigid body mechanics. So, here that part is ruled out. So, we will not be able to recover something like this you study in your undergraduate class. I mean, we teach them, I also teach, but that is not recoverable. So, we should know the limitations of what we are doing. So, if you wish to solve fracture mechanics problems, which I do, okay, I make my living by solving those problems, but I get only approximate solutions. So, okay, so now I have a particle x and I have another one neighboring x plus delta x. So, I'm looking at 2 neighboring particles. They are very close to each other, and I will soon make assumptions as to how close or how apart they are. So, we apply loads to it, which is equivalent to I was pulling it, and what will happen is this body will change shape. So, P goes to P prime and Q will go to Q prime. So, this vector PQ now becomes P prime Q prime. So, I have rotated it and changed its length. So, as I said before, my goal is not to find the change in length, and if I take a pair of vectors say PQ and PR, then I will be able to find the change in angle between them two. Okay. So that's what we are, that's where we are headed. But the constraint is deformations can be large, and that's why I was showing you pulling my arm. We are not going to constrain ourselves to small strains, small deformations. Because this is the title of the course was nonlinear. So this is nonlinear stuff. So it can be large deformations. Okay, so now I need to tell where P prime is and where Q prime is, and I use again their positions in space, and I can use different coordinate system. So this is a particle at x, and this is x plus delta x. So I'm not necessarily using the same coordinate system, but I'm still using rectangular Cartesian coordinate system. Excuse me. There is nothing wrong in using rectangular Cartesian coordinate system. In some problems, we like to use, looking at the shape of the body, say cylindrical coordinates, and if it is a sphere, spherical coordinates. That simplifies the description of the body. But as far as the fundamental equations are concerned, you can work everything in terms of rectangular Cartesian coordinates. And same thing, you can solve the problem for a sphere in rectangular Cartesian coordinates. Actually, many commercial softwares, they do it in rectangular Cartesian coordinates. Okay. So the next thing is that we are going to say that the position x can be described, but actually this is also a vector. The position x can be described, can be expressed as a continuous function of x in the reference configuration and time t. So if I know how my function f depends upon x and t, I'm done. Okay, this is the $1 million or crore rupees question. That's how we will make our living, both in solid mechanics and fluid mechanics. Our job is, given the shape of the body in the reference configuration, which you can say undeformed state. So given the shape of the body in the undeformed state, given the material of the body, whether it's bone, you can say, or it's my soft tissue, or it is copper or steel or rubber, or tires. I mean, material has to be. So this is a direct problem. Direct means that we are given the shape of the body before loads are applied. We are given the material of the body, and we are given the loads applied to it. How long will this body last? Will it last for 1 year, 10 years, 100 years, 1 minute? That is the question. Okay. So it seems very innocent, like it's a very simple problem, that you go to the doctor, you describe the symptoms, and the doctor should be able to tell you what is wrong with you. And in 99% of the cases, doctors are also making guesses based on the previous experience. They prescribe you medicine, it may or may not work on you. There is no guarantee of that, because whenever the drug administration approves medicines, they approve it based on the fact that it works for more than 50% of the people. There is no guarantee it works for 100% of the people, no. Otherwise, no medicine will be approved, no drug will be approved. So in our case, of course, we don't have that issue, because we are saying x is a function of big X and time, but we have other uncertainties in the problem. When I said how long will the body last, so I need a criteria. When will it die? When will it fail? And that's where the uncertainty comes in, because we don't know if there is a crack developed inside the body, how will that crack propagate? And that's basically what's going to cause fracture or failure. Okay, so for the time being, I was going to say I'm going to keep time constant, but yeah, let me say that. Okay, for the time being, I'm going to keep it constant, which means I'm not, I'm comparing this shape with that shape. So I'm not, at this time, I'm not worried about the time variation. We will, okay, we will, because otherwise that will be only half of the story. No, we will worry about time, but say for the next 1 hour or so, we are not. So time is constant, so this is only so these are really 3 equations, because x is a vector. So I could write this as xi is a function of f, and so these are really 3 functions, you know, f1, f2, f3. They give me x1 coordinate, x2 coordinate, and x3 coordinate. Is it okay? No, mechanics people are very sloppy. In mathematics department, I will need to use f1, f2, f3. So I will have to write 3 functions. But mechanics people are sloppy, and they say instead of writing this, I'm going to write it as xi equal to xi times x is a function of big X. So the reason I said sloppy, excuse me, the reason I said sloppy is because this xi stands for a function. This is this I'm using it for f here. This is the value. So that's why I'm saying we are sloppy. I mean, it's not only me. I wish it were only me, but if you open books or read papers, you will see it. So it's better for me to introduce its sloppiness right now, so you are used to it, rather than you are going out and next week you find out, hey, they are using xi equal to xi of x, but he never said anything like that. Right? So this is sloppiness. It's not neat mathematics. But the problem is there are so many symbols we will have to use that we will soon run out of f, g, h, i, j, k. There are only 26 of those. So we will, unless we go to some different language, we will run out of them. Okay, so now this is the value, which is like numerical value 1.1, 1.2, 1.3. This one is a function of x. Okay. If I plug in this function, the value of point, the coordinates of point q, I should get this value, right? So let's do that. So let's say then xi plus delta xi equal xi x plus delta x. So what we are saying is this is a unique function of x1, x2, x3. Unique, I did not mean it's one function, but if you plug in the value of x, you get the value. If you plug in the value of uppercase x, you get the value of lowercase x. So, if you plug in the coordinates of the point or the particle in the reference configuration, you get the coordinates in the present configuration. And our goal is to find this function f. Also, now instead of putting these arrows, I am going to again go back to the index notation, and now my uppercase index L takes values 1, 2, 3. The reason I used uppercase is because those refer to coordinates here, and lowercase refer to coordinates here. That is why I am making a distinction between the two. Uppercase means you are finding the position of the particle in the reference configuration. So, those are names of the particles. Lowercase means you are finding its position in the present shape, in the present configuration. Shape or configuration mean the same thing. Okay? Any questions about this? I'm about to go to finding p prime q prime. So, any questions about this? Okay. So, from these two equations, if I want to find p prime q prime, the ith component of that, which means I equal to 1, I equal to 2, I equal to 3, right. So, what is this vector p prime q prime in the figure? Yes? Small delta x. Great, good. So, that is little delta xi, and that is basically xi xl plus delta xl minus little xi of xl. So, I subtract, this is my p prime, this is q prime, or you can say this is op prime, oq prime, that is what they are. So, I am subtracting the vector op prime from the vector oq prime. So, I get a vector p prime q prime, triangle of addition, right. And please speak up. You have a question? It's okay. Okay, because you are looking at his notes. So, to me it seems maybe you cannot see my handwriting there. Okay. There is no. It's all vector algebra, right? Okay. Now, how many of you have? Well, I should not say this way because all of you have heard of Taylor series expansion, right? So, that is what I am going to do. Use Taylor series expansion. So, what Taylor series says is that if you take y and if you a function, and if you expand it about the point y where h is a very small number, then this is equal to f of y plus h df over dy evaluated at h equal to 0 plus h square over 2 factorial d square f over dy square. Again, this is evaluated at h equal to 0, and you keep on going. So, it is an infinite series, and depending upon the value of h, the accuracy will depend upon the accuracy required will depend upon how many terms you want to keep. Okay, so in our case we are going to say this is equal to then xi. I am evaluating at xl plus delta xi over delta xl. I evaluated at delta xl equal to 0, which really means point P times delta xl plus these 3 dots. Again, you cannot put 4 dots, you cannot put 2 dots. It is a mathematical convention. that for saying it's continued, you have to put only 3 dots. It's a mutual agreement among mathematicians. It's not my invention, and I cannot violate it. So, we have agreed on this. So, it's 3 dots, not 4. So, 3 dots minus this is this one. So, the first term I expanded in terms of Taylor series, and then I am subtracting that one xi. Any questions? Okay. Now, I am going to take, but before I say that, what is this vector equal to in terms of something on the screen or chalkboard or whiteboard? PQ, very good. It's PQ, right? I told, when I was pulling my skin, I said you draw a line 1 centimeter long, right? So, what is this? What if I drew a line 1 nanometer long? Nano is 10 to the minus 9. So, if I drew a line 1 nanometer long and it became 1.1 nanometer, I can still find the change in length, right? I mean, I do not have to draw 1 centimeter. 1 centimeter only helps me with my naked eye. I can see how much it has elongated. But if it is if I draw 1 nanometer, I can use a scanning electron microscope to see how much it has elongated. And if I have a more sophisticated equipment, like say an optical instrument, then I can go to the wavelength of light. Because if I will pull it, then I can throw or polarize light on it and see whether it has elongated or not. So, the accuracy of my measurements depends upon the instrument I have. But I am only interested in change in length per unit length. I am not interested in the absolute value. So, I am interested in change in length per unit length. So, I can take this h here, which all of you told me correctly, this is length PQ. So, I can take P and Q very close to each other, as close to each other as I like, so that the second order term here delta x square is negligible as compared to this term. The argument is the following: I am not saying that this quantity, I am not saying that this quantity has to be small. I did not say a single word about this derivative, right? Supposing this derivative is 10, but then I can take my PQ as 10 to the power minus 20. If I take 10 to the minus 20 and assuming my next second order derivative is also finite, this term will be 10 to the minus 40, which is negligible as compared to 10 to the minus 20. And if you do not like 10 to the minus 20, take it 10 to the minus 100. In calculus, you do that all the time, take the limit as h goes to 0. You do not ask the question, when you say h goes to 0, what do you mean? Is it h 10 to the minus 10 or minus 100 or minus 50? I am interested in finding the ratio of final length to initial length. Okay, that is what strain is, right? This change in length per unit length. So, to find the final length, to find this ratio, what I am saying is I will start with a very, very small length, so small that I can neglect the second order and third order and higher order terms. Is the argument making sense? We did not say this derivative has to be small. That is the key point. I did not say that the magnitude of this derivative has to be small. All I am saying is I will take these 2 points P Q very, very close to each other, because I want to find what is the ratio of P prime Q, the length P prime Q prime to the length P Q. Okay. So, if you agree with that, then I can neglect these 3 dots terms. This cancels with that. So, we get this delta xi equal to f I L. This is evaluated at point P times delta XL. So, this is the reason I put still equality is under the assumption I just stated. I am neglecting the quadratic terms in delta x, cubic terms in delta x, by taking delta x to be extremely small, but I am not requiring that this derivative of little x with respect to big X be small. No, this is very critical, because if you do not agree with this assumption, we cannot proceed. And not only we cannot proceed, we cannot, well, I should not say we cannot solve any problem. These days, at present time, is fashionable to take the second term here to consider the second term and then neglect the other higher order terms, and people call these as strain gradient theories. So, it is quite fashionable. When I say fashionable, is that you include that term and people publish a paper. So, another very fashionable term is functionally graded materials. So, it's the reason I am saying fashionable is because there is not much new mechanics being introduced. So, it is basically you buy a dress and it has a different pattern on it, but the basic fabric is the same. So, that is what I mean, that is fashionable, but it is easier to publish. Anyway, there is a flood of papers. The basic work was done 60, 70 years ago, but at that time there were no computers, or the computing power was very limited. Okay. So, if you notice here, I have put this P, because this derivative is evaluated when delta x is 0. So, this derivative is being evaluated at point P. It is very critical that we are evaluating this derivative at point P. So, whatever we will find from this derivative will be applicable at point P, but P is an arbitrary point. I did not say you choose P this any specific way. So, it is an arbitrary point, that means you can do it at every point in the body. All difficulties may come at the boundaries, but in the interior there is no problem. And this f has a name. So, this is called deformation gradient. So, it is one of the basic quantities in continuum mechanics, deformation gradient. Most of what we will do, we will derive from this f. Any questions about this? Okay. So, I said we want to compare lengths. So, I find the length of this. So, let us say the length is ds square. The length of this is ds. The length of the vector p prime q prime is ds. I want to find ds square. How do I do it? Dot product. Very good. So, I take the dot product of p prime q prime with p prime q prime, which really means is p prime q prime I, p prime q prime I, and if I delta XL, not D. So that's PQ, and then I have another F M PQ. See, it's P prime Q prime. So in one case it is FIL delta XL, and then I cannot use L again because then I will get L 4 times. So I'm changing it to M and M. Okay. Now again to save some writing, and actually it's not only saving writing, it's giving credit to a person. So this quantity FIL FIM. So what is this equal to? Now it is summed on I, right? Because I is repeated. How many? If you look at F, I goes from 1 to 3, L goes from 1 to 3. So it's a 3 by 3 matrix. I mean, you can write it as a 3 by 3 matrix. It's 9 quantities, and you can write them as a 3 by 3 matrix. This is also a 3 by 3 matrix. I summed. So the end result is going to be 3 by 3. So if I say this is equal to C L M, this is a standard notation. When I say standard, I mean like 90% of the authors use it. So I am setting FIL FIM equal to CLM, and you can say I can put 3, that means definition. Now I want to evaluate this. I mean, as far as my work is concerned, I can proceed further, but supposing I want to do computations, I want to compute it. How will I evaluate C if I give you F? And I think all of you agree, or most of you at least agree, this is 3 by 3, this is 3 by 3, this is 3 by 3. Because L goes from 1 to 1, 2, and 3, and M is 1, 2, and 3, and I summed. So can we figure out what is happening on the left side? F transpose F. So it's really matrix multiplication. So you take a 3 by 3 matrix, multiply it by a 3 by 3 matrix, you will get a 3 by 3 matrix. The only thing we have to remember is that this one, the summed index here is the first index. So if you say this is row, this indicates row, this also indicates row. But when you multiply matrices, you take the column of the second matrix multiplied with the row of the first matrix, right? And if we do that in this case, so this it will be like A I J B J K. The summed index comes next to each other. The index which is being summed appears next to each other. So that's what indicates you take the column of this, multiply with the row of that. But here we don't have that. So I need to get I next to I. And as you correctly said I take the transpose. Transpose means you interchange rows and columns. So, if I take the transpose, then this thing will be F transpose L I F I M. When you take the transpose, then you interchange rows and columns. That is what I did. So, if you adopt the convention that the first index implies row, second index implies column, then this is what. Okay. So, if we agree with that, then I can say that F transpose F equals C. So, instead of using index notation, I could say F transpose F equals C. So, when if you are writing computer code, you could say F transpose multiplied with F equals C. This C has a name. So, this C is called right. Whenever I use the word right, there must be something left. It will come. Otherwise, I would not have said right. So, this is right, Cauchy, and this name you will hear a lot in this course. So, Cauchy is roughly speaking father of continuum mechanics. He is a man, so that is why I said father. Otherwise, I would have said mother. So, it is right Cauchy Green tensor. So, there left Cauchy Green tensor will come also. Okay. So, what we wrote then, we have here C L M P Q L P Q M. So, from F we really have gone to C now. The property of C is symmetric. Like one property of C is symmetric. If you interchange L and M, nothing changes. Or if you take, say, C is F transpose F, and if you take the transpose of this, and thus F transpose F, because transpose of a transpose is the matrix itself. So, C is symmetric. Another property of C is, what do you think, can this value become 0? Can CLM, PQL, PQM become 0? Is my question making sense? So, first of all, like CLM, PQL, PQM is a scalar quantity. It's a number like 1.05 or 2.3, but can it be 0? Why cannot it be 0?
Because of assumption that 2 points can't.
Very good. Because of the assumption that 2 different points will always occupy 2 different places. So, the length of the vector p prime q prime cannot be 0. And that property is very critical because that tells us eigenvalues of C cannot be 0. Actually, eigenvalues of C must be positive, because C is symmetric, which means eigenvalues of C are real. A symmetric matrix must have real eigenvalues. Eigenvalues of a symmetric matrix are real. So, this is a 3 by 3 matrix, it has a 3 real eigenvalues. Real does not mean it cannot be 0, real only means there is no imaginary part. But if this quantity is positive for every PQ, then we say this matrix is positive definite, and if the matrix is positive definite, its eigenvalues must be positive, no zeros allowed. So, they must be positive. So, this is a result in linear algebra, it is not okay. Now, I will come back to the claim that I want to find really change in ratio of lengths, right. That is what I mentioned. So, that is why we use the argument that if delta x is not very small, you make it even smaller. So, I divide both sides by ds. This is in the reference configuration, this is length of PQ, and little dx is the length of P prime Q prime. So, are we on the same page, which means are we communicating? So, what about this quantity now PQL over ds on the right hand side? What about this one? What can we say about this? And of course, you have learned it. I mean, you learned it in vector algebra, which may have been quite a long time ago. So, what this quantity has something, some name, some interpretation. It is a unit vector. It is a unit vector along PQ. So, that symbol, that index L 1, 2 and 3. So, they give you components of the unit vector along PQ. Now, the length of PQ is not coming into picture, right. When we are comparing final length over initial length, all we are looking at is a unit vector along PQ. But of course, we have made the assumption that these higher order terms were negligible. So, this thing is now CLM, NL, NM, where N is a unit vector along PQ. Well, that is how we denote unit vector, right, vector over its length. So, if I know f at point x, which so if I know f at point x at this point, which is 3 by 3 matrix f deformation gradient. So, if I know f at point x, I can find C, which is like f transpose f. We know how to multiply 3 by 3 matrices. From C, you give me any vector you like passing through point x. There are infinitely many vectors passing through point x. I can find the ratio of final length over initial length for all of them. All I have to do is you give me n, I compute this. When I say you give me any vector starting from P, which basically you are giving me n, 3 components of that vector. So, give me 3 components of the vector, I take this product on this scalar quantity, and I get the final length over initial length squared. Good. And if you want to find engineering strain, which we sometimes are interested in, then that is square root of this. And if you want to find change ratio like change in length over initial length, So we got the traditional definition of engendering strain. That's change in length over final length, like little ds minus big ds over big ds. That's this quantity. Is it okay? Okay, now I have a different question. So I'm still at point P. We will be at point P for a while. But remember, point P is arbitrary. So it's not that we have set aside like this point must be here or there. So I'm at point P. Now my question is a little bit different. I want to find out. I think you have a question. Please speak up. Speak up because you are looking at something previous one, which means we missed something, right?
No, sir, I was just going
It's okay. There is nothing wrong in asking anything. Okay, it's up to you. But I'm not offended if you ask me anything which I covered earlier. Okay. Okay. So now I'm interested in the following question. Which direction through point P, along which direction through point P is my change in length per unit length maximum? I want to find out, if I take unit vector, say, then that means I have to be on this circle, right? So which one of these line elements is stretched the most or the least? Both of them have the same answer. Am I making any sense? Is my question making any sense? So if, like before you deform the body, you draw a circle on it. Okay, so it's a small circle, but it's large enough that you can see it. This circle, when you deform the body, will become an ellipse. And if you have a three-dimensional picture, you will draw a sphere, and it will become an ellipsoid. So if I just talk about two-dimensional, so it's an ellipse. So I want to find major axis and minor axis. So major axis will have the maximum elongation, minor axis will have the minimum elongation. That's what I want to find. Is the question making sense? Because unless you know what we are trying to do, doing math is not going to be helpful. I'm sorry? Yes, you already answered my question. Yes, you are right. So how do we get it? Like how do we know it is the eigenvector? That's what now I want to prove that. Your answer is correct. Yes, very good. Okay, so that's the question now. Now we want to show, because whatever proof I give you now, I will use it tomorrow or day after tomorrow for stresses. So it's the same, mathematically it's going to be the same proof, but the language will be different. Instead of saying which line element is stretched the most, I'm going to use some like which element, which plane has the maximum normal stress. Okay, so now, so we want to find so the problem is find n such that this symbol, I don't have to introduce it. Okay, such that n is a unit vector, So that's what it says, NL, which means N1 square plus N2 square plus N3 square equals 1. So it is a unit vector, and ds over big ds, let's say squares, is maximum. So I did not write maximum, I just wrote max. So it's maximum. Okay, so that's the problem. Now, just 5 more minutes. Okay. So to solve this, we are going to use the method of Lagrange multipliers. So Lagrange is a mathematician. Like we heard Laplace in the morning. Lagrange is equally famous as Laplace. Same for Taylor. So if like professor gave you motivation to get a name, a theorem or something named after you, so aim for one of these guys: Lagrange, Taylor, Laplace, Hildebrand. There are Cauchy, Green, Truesdell. So there are many people like that. Okay, so what Lagrange proposed was that you write your constraint as something equal to 0. You write your constraint as something equal to 0, and you modify the function you want to maximize or minimize by introducing a Lagrange multiplier or something unknown times the constraint. So I want to know, instead of maximizing this quantity, I'm going to maximize this one. So I have defined a new function. It's a function of 3 variables, N1, N2, N3. See, our problem was find N1, N2, N3 such that this condition is satisfied and this quantity is maximum. Now I have the same quantity, but I have introduced another quantity. So now this one becomes, instead of a function of 3 variables, it is a function of 4 variables. So it's a function of 4 variables, and I think we will pick it up from. I think nobody is going to erase this, right? This whiteboard. So we can pick it up after lunch. So I think it's like 1:20 now. So we will start at 3. Is that enough time? So we can start at 3 o'clock and then go up to